Good evening, everyone. I'm Alok Jha. I'm a journalist at The Guardian. I'm going to speak just for a couple of minutes just to introduce Sean. You're here to see him, not me. I want to tell you a bit about Sean Carroll. You obviously know enough about him to be here, and you've hopefully read his book, or you're going to read his book after you've bought it outside afterwards. But Sean is a theoretical physicist at Caltech. This is the institution of Feynman and many other Nobel Prize-winning scientists. He is a specialist in dark energy and general relativity, amongst many other things. Until recently, he's also a very prominent blogger at Cosmic Variance. This is a group blog, very famous. He's got his own blog now, and he's a big voice in the world of science communication. He's also appeared on lots of TV shows in the US, TV shows that I hope one day will be shown here, including Through the Wormhole with Morgan Freeman. I want to know if he knows Morgan Freeman later on. He does. Get the stories about that later on. And he's also been, most importantly, on the Colbert Report, which, as we all know, is a very important topical news program in the States. He's also science advisor to many, many Hollywood blockbusters. If you've got questions at the end of this about the science in the Avengers, he is the man that made all that happen, so you can ask him all those questions, including what's in Avengers 2. Sean is also, of course, an accomplished author. In January 2010, he wrote a book about the arrow of time. It was called From Eternity to Here. And his latest book is about the Large Hadron Collider, the search for the Higgs Boson and the people that made it happen. He might even be able to tell us what it is they actually found at the Large Hadron Collider last year in July, this Higgs-like thing. What is it? So please welcome Sean to talk about his book, The Particle at the End of the Universe, How the Higgs Boson Leads Us to the Edge of a New World. Sean.
Thanks, Alec. Thanks, everybody, for coming here tonight. Thanks to the Royal Institution for inviting me to speak at such a historic venue. And much like Michael Faraday sitting in the audience when Humphrey Davy was giving talks way back in the day, you too can tweet what is going on as in real time with the hashtag #RIParticle. And I very sincerely want to say how wonderful it is to be not only right here, where all these events happen, but also in London. The spirit of the city and the country is a little bit different than in my home country of the United States, which is sort of like the little baby cousin of England. And one of the ways in which this manifests itself is when I am on the Twitter machine myself, and I see things like London for Lovers, suggesting that the particle at the end of the universe, that's the fascinating date for the science lover, so I hope that some of you made it. You presumably know why I'm here and why you're here. On July 4th this year, I was lucky enough to be in Geneva, Switzerland, at CERN, the giant particle physics laboratory, and home of the Large Hadron Collider, the largest machine ever built by human beings. And what was happening on July 4th were 2 PowerPoint presentations. Very exciting. Sufficiently exciting that there were plenty of physicists in their 20s camping out overnight to get good seats in the lecture hall, just like this. I mean, none of you guys were out there. I was here at 5 a.m. and you were not there camping out for the good seats. But they were there. They wanted to not miss these PowerPoint presentations. It was like a rock concert with a lot more Macintoshes open on their laps. And then in the actual audience for the PowerPoint presentation, there were physicists in their 80s breaking down with emotional reaction to what was being told to them. And what was being told to them, of course, is that we had discovered a new particle of nature, something that we think is what we've been looking for many decades now, the Higgs boson. But you know, there's particles, we've been discovering particles for a long time. Why is it that this particular event was so important to so many people? So the question of the talk that I'm going to try to answer is, what's the big deal? Why do we care so much? Why did people line up ahead of time, camp overnight in not very comfortable conditions, just to get third-row seats for a couple of PowerPoint presentations in the early morning in Geneva, Switzerland? Well, physicists knew this was coming. It was not a surprise. We've been looking for this particle for a long time. We had hints that we were getting close to it. Part of the result of these hints was that I wrote a book about the whole thing that you can buy right out there in the lobby. And so we weren't surprised, and yet We have done a very, very bad job of explaining why this discovery is so important. It's not that we haven't tried. Physicists have tried to come up with sort of clever labels and things to sort of impress upon a more general audience that this is a big deal. Some of those labels are frankly not a good idea. And we're regretful that we have invented those labels, and we've moved on from those. But we still haven't really quite nailed it. And I have a theory as to why we are not able to explain the Higgs boson very well. And the theory is that we use the wrong starting point. The kind of starting point we use to discuss particle physics is this guy. Does anyone know who this is a portrait of? Okay, you don't know, believe me. This is purportedly a portrait of Democritus. Democritus, an ancient Greek philosopher 2,500 years ago. Essentially, Democritus was the first theoretical particle physicist. He was the guy who really pushed an idea that also his predecessor also pushed, but his predecessor didn't write anything and publish or perish in the academic world. So Democritus was the first to commit to print the idea that the world is made of atoms, as he called them. What we would now call elementary particles, because our 19th century forebears skipped ahead and called things atoms even though they weren't truly elementary. But the Democritian idea is really so astonishing that we should step back and really appreciate what he was saying. You know, if you look around you, there's air, there's wood, there are desks, there's metal, there's cloth, there's other human beings. These substances appear very different, right? They have different properties. They look different. They react differently. And yet, Democritus says they're not fundamentally different. They're just different arrangements of the same underlying stuff called atoms. And that idea, it took a long time to get it right. It turns out to be right. And what we now, the descendant intellectually of Democritus's ideas are what we call particle physics. Now, of course, because he lived 2,500 years ago, there's no surviving image of what Democritus actually looked like. All there is a surviving nickname that he had, the laughing philosopher. So because that was his nickname, he was a very, very popular subject for portraiture in the Renaissance, because the portrait painter could just paint a self-portrait of himself laughing and then label it Democritus. So this is Rembrandt's self-portrait labeled Democritus. We have no idea what Democritus looks like, but we give him credit for launching the bandwagon we currently know as particle physics. The problem is that particle physics as an idea is not the right way to think about the Higgs boson, and that's the stumbling block that we're all faced with. So rather than go back to Democritus, I like to talk about the Higgs boson by referring to these guys, a younger generation of important thinkers. These are Americans. You might not be familiar with the phenomenon, as we might say. This is the Insane Clown Posse. These two young gentlemen, this is Violent J, and that's Shaggy 2 Dope. These are not the names that their mothers gave them, but they're artists. And this is a thing in the United States. These guys paint their faces, and they have followers called juggalos who have big events, and they're rappers, they're musicians. So a couple of years ago, they shocked the world by, most of their songs involve rather outre activities, violence, they're partying, that's what they do. So a couple of years ago, they shocked the world by having a reflective tune about the miracles of the world all around them. The tune was called Miracles, and if you read it, they say, "I see miracles all around me. Stop and look around, it's all astounding. Water, fire, air, and dirt. Frickin' magnets, how do they work?" Frickin' was not the word, but you can Google it. You can look it up. Now, the boys received a certain amount of disapprobation from the scientific community by saying, "Magnets, how do they work?" We know how magnets work. Much of it was demonstrated right here where I'm standing many, many years ago. So we do have a working scientific understanding of the esoteric phenomenon known as the magnet. But I nevertheless want to give them a little bit of credit, because even though we understand it, even though we have equations we can attach to this idea, it is still astounding. Think about a magnet. A magnet is something you can attach to a piece of metal, right? It will stick to it, a refrigerator or so forth. You can stick lots of things to lots of other things. You can stick pieces of tape or gum or whatever. But when you stick a piece of tape to the refrigerator, the tape has to touch the refrigerator in order to stick. The gum has to touch the refrigerator in order to stick. A little insect or gecko walking up the wall needs to touch the thing in order to stick to it. A magnet, if you hold it close to a piece of metal, you can feel it pulling before it touches. The magnet reaches across empty space and exerts a force, and the refrigerator exerts a force back, according to Sir Isaac Newton, that pulls the two things together. They don't need to touch each other. How is that possible? How does the magnet know that there is a refrigerator nearby that it should be attracted to? So the answer, well, I'll tell you the answer, but first I'll tell you that it's not just these modern day philosophers who are puzzled by this. There's an older natural philosopher who was puzzled by this. We've already given him a name. Sir Isaac Newton was very puzzled by this phenomenon, which is known as action at a distance. Newton was interested in gravity, not magnetism, but it's the same thing. The Earth exerts a force on the moon or satellites orbiting the Earth. They're not touching each other. The Earth seems to push out across empty space to exert this force on things in its vicinity. Newton said that you can understand gravity throughout the universe in terms of an inverse square law. The force of gravity becomes weaker and weaker as you move away, as the distance between the two objects squared, okay? So, but he was very worried. In fact, he said that this phenomenon of action at a distance made no sense, even though it was part of his theory. To Newton, the action at a distance aspect of his extremely successful theory of gravitation was much like contemporary physicists think about quantum mechanics. An incredibly successful phenomenology, a set of rules that fits the data to wonderful precision, and yet deep down in our bones, we think it makes no sense. We can't quite make sense of it. And Newton's problem with action at a distance was actually solved by another philosopher/scientist, Pierre-Simon Laplace. Laplace came up with a new theory of gravity. It turns out it wasn't really a new theory of gravity. It was the same theory as Newton's. No one talks about Laplace's theory of gravity. It's a way of rewriting Newtonian gravity, but it's a way that gets rid of the action at a distance. What Laplace says is that instead of just thinking about random forces between objects very, very far away, imagine there is a field filling the universe. And what that means mathematically is just that at every point in space there's a number. The value of the field. Just like the temperature of the air in this room, at every point there's a value, the temperature at that point of the air. But this is not some phenomenology of the matter, this is just a fundamental feature of reality, the gravitational potential field. And the way it works is that near the Earth, here's the Earth, and this curve is the value of the gravitational potential field. It's pushed down by the Earth, then it just climbs up smoothly, and the gravitational force that an object feels is just the slope of that line, the amount by which, the rate at which the gravitational potential field is changing. So there isn't anything acting instantaneously and spookily at a distance. There's a smooth change from the position of the Earth to the position of the Moon. The gravitational potential is very low here near the Earth, and it climbs upward as you go toward the Moon, and that change keeps going forever. So the Earth is affecting something that stretches throughout the entire universe, the gravitational potential field. There's nothing acting instantaneously across a very large distance. And this idea of a field turns out to be quite useful. It wasn't just Laplace. In fact, in the minds of physicists, the person whose name is most closely attached to the field concept is Michael Faraday, who gave the lectures right here in this very spot. He said that the way to think about electricity is in terms of the electric field. And that's what we do these days. We talk both about particles and about fields. In one sense, a particle and a field are the opposite of each other, right? A particle is something that has one location. Here's the particle, it's nowhere else. A field is the opposite of that. A field is everywhere. At every point in space, there is a value of the field. So if you look at the picture up here on the left, these are tracks of particles through a cloud chamber. They're individual lines. A particle moves through the chamber and leaves a little trail behind. They're curving because they're moving in a magnetic field. On the picture on the right, there is a magnet. You can't see the field lines directly, but they're traced out by the little iron filings that are in the vicinity of the magnet. So you can visualize the fact that around this magnet there's an invisible field filling space. So particles and fields are the two things that physicists talk about when we talk about the ingredients that make up reality. And if you have a tiny bit of physics education, you may have come up against the question, is light, for example, a particle or a wave? A wave is sort of a vibration in a field. So what is more important? Is it the particle aspect of reality, or is it the field aspect of reality? It's fields. That's the answer. It's not a mystery. They always tell you that question. They never tell you the answer. I went decades of my life. So what's the answer to this? This is the answer. It's fields. Any questions about that? So I'm going to go into a little bit more detail, but not too much. But this is the crucial slide, okay? There's no more information. There's nothing more to come on this slide. The reason why the Higgs boson as a concept is hard to grasp is because you need to stop thinking of the world in terms of particles. You need to start thinking of it in terms of fields. And you say to yourself, well, but things like this table are made of atoms, and atoms have electrons and so forth in them, and the electrons are particles, right? There are particles in the world. No, there aren't. That's the secret that we physicists have never told you, but here I am, I'm going to tell you right now. The reason why you're allowed to think of particles is because of quantum mechanics. The world is made of fields, but quantum mechanics says when you look at the world, you don't see it directly. What really exists, according to quantum mechanics, is immensely richer than the things we can actually observe. So the reason you think that there are particles is because there are actually all these fields filling empty space. At every point in space, there's dozens of little vibrating fields in front of you. But quantum mechanics says that when you look at the fields closely enough, they resolve into individual particles. So on the picture on the right here is from David Deutsch, an Oxford physicist, one of the founders of quantum computation theory. And he says, imagine you are a frog. He doesn't care whether you're a frog or not, but frogs, it turns out, have slightly better vision than human beings do. And what that means is that frogs can see individual particles of light, photons. You're all seeing light from the light bulbs here, from the screen and so forth. Light is two things, right? Light is a wave in the electromagnetic field. So there's a field filling space at every point here. There's a little electric field, a little magnetic field. They're vibrating, and that's the light that is coming to you. But quantum mechanics says you look at that light very carefully, and it turns into individual particles called photons. Photons are the particles that you see when you look at a wave in the electromagnetic field. So if you think a light bulb or a lantern and someone is moving it away from you on a dark night, it gets dimmer and dimmer as it goes out in the distance. And to you, it just fades away. But if your vision were better, if you were as good as a frog at looking at things, it would stop getting dimmer and start flickering. So there's a point below which the brightness never goes. It just becomes more intermittent. And what's happening is you're making a transition from seeing lots of photons all at once to seeing individual photons hitting your eye. The reason why light resolves into photons is because quantum mechanics says that when you look at it, that's what you see. The relationship between particles and fields is that fields are what the world is made of, particles are what you see. So the atoms in this table, the electrons, the quarks, the protons, these are all vibrations in fields. There's a quark field that is vibrating. You look at it, you see quarks. There's an electron field that is vibrating. There's a neutrino field that is vibrating. There's a gravitational field that is vibrating, and so on and so on. That's quantum field theory. It is the very heart, the central organizing concept of modern physics. And no one tells you until you buy my book. All right. So let's put this in a little bit of context. Let's imagine where we were a few decades ago in the 1930s at the birth of particle physics, which you now really know should be called field physics, but we'll stick with the old way of talking about it. In 1935, you could have been accepting if physicists were getting ahead of themselves a little bit, because they had these three particles. They had this vision of what the universe was. They were atoms that made up this table, the air, you and me, and they knew what the structure of the atom looked like. There was a nucleus in the middle that had protons and neutrons, big heavy particles stuck together. There was electrons orbiting on the outside, and the electrons are attracted to the nucleus by the electromagnetic force. There was also the nuclear force inside the atomic nucleus that was holding the proton and neutron together. And then there's gravity that is holding the whole shebang. Gravity says that every particle pulls on every other particle. And you look at this picture, circa 1935, and you say, that's a picture that seems to fit reality pretty well. Out of these ingredients, you can make everyone you ever met. You know, the people you like, the people less so, they're all protons, neutrons, and electrons arranged in different combinations. We have, nevertheless, science did not stop. We kept doing things. We discovered more particles, and we complicated the picture a little bit. Not too much, but a little bit. For one thing, we looked inside the protons and neutrons, and we found that there were these things called quarks. The up quark and the down quark combine in different ways to give you protons and neutrons. So as far as that goes, there was not an increase in the number of particles, but instead of proton and neutron, we say up quark, down quark. There was an increase in the number of forces. We went from one nuclear force that held the proton and neutron together to two different nuclear forces. The strong nuclear force that holds the quarks together, the weak nuclear force that you can go through your everyday life and never notice. The weak nuclear force is weak. That's why they named it that way. But nevertheless, it is important. If you walk outside in Los Angeles, we have this thing where you walk outside and you look up into the sky, there's a bright spot that is shining down light called the sun. And sometimes it appears in England as well. But the force, the way that that bright spot called the sun is giving out energy is essentially from the weak nuclear force. When two protons come together, one of those protons can convert into a neutron, spitting off another particle called a neutrino, and then they stick together and make a little atom. Energy is released, and we have nuclear fusion. So that's the new picture. Now, for reasons we still don't understand, these four matter particles, the neutrino, the down quark, the up quark, and the electron, four particles that make up matter, turn out to be a single family of particles. And there's another family and another family. There are three generations, if you like. Nobody knows why that's true. It's the same pattern repeated 3 times. That little bit is a mystery. Otherwise, we have this picture, and if you want to make it a little simpler, I made a flow chart for you, and you can go through the flow chart. You want to know what particle you are, here's the little questions you should be asking yourself. So you have the 3 generations. Here's the up quark, down quark, electron, and its neutrino, but then there are other generations of matter particles on top. There are bosons, and then way up, all by itself in the corner, there's this lonely little thing called the Higgs boson. So why in the world, with all the success of this picture of particle physics, do we need another particle, another field pervading the universe called the Higgs boson? Well, it goes back to the 1950s and 60s when particle physicists were trying to understand those nuclear forces, okay? If you think about it, it's the nuclear forces that you don't notice in your everyday life. Electromagnetism, every time you open your eyeballs, you notice electromagnetism. Light is an electromagnetic phenomenon. Heat is an electromagnetic phenomenon. Remote controls, laser pointers, electromagnetism all the way down. Gravity, you certainly notice. That's easy enough. You don't notice the nuclear forces. And why is that? It's because gravity and electromagnetism extend over very large ranges. They can go, in principle, infinitely far. They're important not only in this room, but in cosmology, in the structure of the universe itself. Whereas the strong and weak nuclear forces only stretch a very, very short distance. And that made no sense from the point of view of the 1950s. We understood gravity and electromagnetism, but if we followed our noses and said, well, maybe the strong force and the weak force are just like gravity and electromagnetism, we kept bumping up against a prediction that was obviously wrong. The prediction was that the strong force and the weak force should also be infinitely ranged. It was not a coincidence. It was a prediction of the model. And one way of saying that is that the particles that carry the forces, the photon for electromagnetism, the graviton for gravity, are massless. They move at the speed of light. They have no weight unto themselves. So they can just travel throughout the universe carrying the forces with which they are associated. And the math kept predicting that the particles that carry the strong nuclear force and the weak nuclear force should also be massless and therefore should give rise to long-range phenomenon, but they didn't. So this was a puzzle and this annoyed people. They figured it out, and many Nobel Prizes have been handed out along the way. It turns out, just to make the lives of physics graduate students difficult, that nature has chosen to use completely different methods of giving a short range to the strong nuclear force and the weak nuclear force. The strong nuclear force, think about, if I go back to the previous slide, think about that lantern that is being taken far away from you. Just like the force of gravity or the force of electromagnetism is an inverse square law, the brightness of a lantern is also an inverse square law. The brightness goes down by the distance squared as the lantern gets further and further away from you. So somehow what we want is we want a strong nuclear force lantern or a weak nuclear force lantern to be very bright if you're very close to it, and then get really, really dim very, very quickly as it moves away, not gradually like electromagnetism or gravity. So the way it works in the two cases is utterly different. In the strong nuclear force, the particles that carry the force are called gluons, and they are massless, but it's as if someone has put a shutter around that lantern that they're carrying away from you. So all of the gluons bounce around inside the proton or the neutron, and they cannot escape. They're confined, we say. So they are indeed massless particles, but there's a barrier past which they can't go. So if you're looking inside the proton, the strong nuclear force looks really, really bright, and then as soon as you get outside, you barely notice it at all. Nobel Prize a few years ago for this discovery of confinement and the strong nuclear force. The weak nuclear force uses an utterly different idea. It says, what if it's a foggy night? What if, you may have noticed this phenomenon here in England, there's sometimes at night, the air is full of something that gets in the way of you seeing. Fog or smog we have in Los Angeles, it's an advanced form of fog. And what happens is that the light gets absorbed on its way to you. So you see a lantern right up close and you have no trouble seeing it at all, but if you move it further away, you suddenly don't see it. And the reason why is because the light is just attenuated by it keeps bumping into this field of stuff filling space, smog, fog, or what have you. So in the weak interactions, that's how the universe works. There's a thing, a field, a substance in empty space that absorbs the lines of force associated with the weak interactions, meaning that the weak interactions can only stretch a little way before you don't notice it anymore. And what that turns out to predict is that the W bosons and Z bosons that carry the weak nuclear force are massive, are very, very heavy. That is a prediction of the theory, of this obscuration theory. You might guess that this was not the idea of a single lone genius like Einstein. It took many, many sociable geniuses to put this idea together. So here is my attempt to give some credit where it is due. Phil Anderson was a condensed matter physicist who first suggested this idea that there is some sort of obscuring field that makes force-carrying particles get mass. Francois Englert, Robert Brout, Peter Higgs, Tom Kibble, Gerald Gralnick, and Richard Hagen all took Anderson's idea and made it respectable. They made it compatible with special relativity. They wrote down explicit theories and equations that we could go then solve and look for. These guys, Sheldon Glashow, Abdus Salam, and Steven Weinberg, realized that the usefulness of this idea is not in the strong nuclear force, but the weak nuclear force, and they showed how it actually gave mass to all of the particles, not just the W and Z bosons. And Gerard de Tooft was the one who showed that the whole thing was mathematically respectable, that the equations made sense. And once de Tooft came along, he was a graduate student at the time, by the way. He showed all of this made sense. The bandwagon was launched. He and his thesis advisor won the Nobel Prize several years later. So what is this idea? I've said it already, but let me say it again because it is the deep thing that makes the Higgs boson so special, so hard to understand, and so precious to professional physicists. Even in empty space, the Higgs field is not zero. So I already told you that the world is made of fields. There's an electron field, a neutrino field, an electromagnetic field, a gravity field. And if you go far away from everything else in the universe, if you shield yourself, if you're looking at a little region of space which is as empty as it is possible to be empty, the fields are there, but they're just sitting at zero. They're not doing anything. They're at their minimum energy state. They're gradually vibrating a little bit because of the miracle of quantum mechanics. Quantum mechanics says you can't quite quiet down fields to a perfectly quiescent state. There's always a little bubbling and boiling because of the Heisenberg uncertainty principle. But they're close to zero. On average, they're sitting there at zero. So if you were to plot this, here are all the fields in the universe out there in empty space. There's some value that the field has. Here's where you are in space. So electrons, quarks, gluons, they're all just vibrating because of quantum mechanics in the vicinity of zero, close to zero. The Higgs field is different. The Higgs field has the property that when you're out there in empty space and you ask, what is the field doing in this little empty region of the universe, it's not at zero. It is displaced at some constant value. It would take a lot of energy to move the Higgs field back to zero. We say that the Higgs field has a non-zero expected value, even in empty space. So the Higgs is also sitting there quietly, vibrating a little bit because of quantum mechanics. When it vibrates by a lot, we call that a Higgs boson particle. A particle is a substantial vibration in the wave. But even when there's no particles around, there's still the Higgs field. It's everywhere you go. You personally move through Higgs field as you travel through the day. And that's crucially important to how your personal physics works, because all of the particles that you're made up of interact with this Higgs field. The weak nuclear force is attenuated because of the Higgs field, but also the other particles that you're made up of get heavier because of the Higgs field. So if there were no Higgs field, turns out this is a whole long story that most of us just don't want to talk about, so we just talk faster and faster, which is exactly what I'm going to do. Turns out, if you try to make a sensible theory of the weak interactions, you predict that not only is the weak interactions mediated by a massless particle, but the electron is massless. The up quark is massless. All the quarks, all the leptons are exactly massless if the weak interactions make sense if you don't have a Higgs field. We know that's not right. We know that the electron has a mass. Without the Higgs, the electron would zoom around at the speed of light. Why would you personally care about that? Because if the electron were moving around at the speed of light, it would not settle into atoms. Okay? If there was no Higgs field filling empty space, there wouldn't be atoms. There'd be electrons and quarks and so forth, but the electrons would be zipping around like photons at the speed of light everywhere in the universe. They would not settle down, make an atom. There would be no atomic physics. Therefore, there would be no chemistry. There would be no possibility for two atoms to get together. Therefore, there would be no, I know you don't like chemistry, but it's important to you. Because without chemistry, there's no biology. Without biology, there's no life. There are no lectures at the Royal Institution, and so forth. Without the Higgs field, life as we know it would be utterly impossible. It would be essentially, no one knows of a way that you could even get any interesting, complex structure in the universe if it weren't for the Higgs field. But you put a Higgs field there in empty space, now that electron is moving through this thick, treacly-like Higgs field, and it picks up a mass thereby. Instead of zipping along at the speed of light, now the electron keeps talking to the Higgs field all around it, and it gets some heft because of that. It has a mass, it takes effort to get it moving, the electron can now settle down, we can have atoms, we can have chemistry, we can have life. You're getting an idea of why this notion of the Higgs field filling empty space is so important to physicists. Important enough that we built giant machines to go look for it. So just to summarize where we are, the reason why the Higgs field is interesting is because it's based on a field that is not zero in empty space, a purely theoretical construct from 1964 meant to address the question, why are the weak interactions so short range? And ever since 1964, we've been looking for the thing. And the Large Hadron Collider at CERN is the most recent version of our attempts to look for the Higgs boson, the particle that you get when you set a vibration going in the Higgs field. This is a pictorial illustration of what the Large Hadron Collider looks like. This is the CERN airport, the Geneva airport, Lake Geneva. About 1 out of every 16 passengers that lands at Geneva airport is associated with CERN in some way. It's a big deal. It's also underground. You couldn't see it. You notice it's under these buildings. People live right on top of the Large Hadron Collider, zooming underneath them. Many numbers you can attach to show how impressive it is. 27 kilometers around, about $9 billion to make, 10,000 people involved in the construction and operation of the thing. What it does is it takes protons, heavy particles made of quarks, and accelerates them to 99.999999% the speed of light, and then it smashes them together, and we watch what comes out. Okay, this is what particle physics. Particle physics is just, kids grown up given $9 billion. What are they going to do? They're going to smash things together, see what comes out. The interior of the pipe through which the protons move is empty. It's about as empty as they can make it. It's more empty than the atmosphere of the surface of the moon, because you don't want your protons bumping into things along the way. And also, the protons, you don't want them to go in a straight line, because then you can't bring them around to hit each other. So the reason why 27 kilometers is because the set of protons, hundreds of trillions of protons at any one time, are moving around. The total energy of those protons is comparable to that of a freight train moving at top speed. So you want to have magnets that curve the protons around the ring. You need giant superconducting magnets that are colder also than empty space, colder than the universe itself, 1.8 Kelvin. It's a big deal. It took a long time to make it. A lot of credit goes to these guys, Carlo Rubbia, who was Director General of CERN, the European Particle Physics Laboratory, and really insisted that CERN plan on building the Large Hadron Collider, even though the United States was planning on building a competing machine. The United States ultimately lost its nerve, and therefore Rubia was right to do that. And Lynn Evans, a Welsh physicist who was given the task of guiding the LHC from planning to completion. He is the person who is most responsible for the LHC as we currently know it. Now let me pause for a little parenthetical extra talk that you didn't come here for, but I want to give you anyway, because when I give this kind of talk, I love not only talking about the physics and the machines, but also the people, because science is a human endeavor, right? We do things, it's human beings that make science happen. It's not just falling down from the sky. So I like showing you pictures of these people. But you will have noticed all these pictures I'm showing you of the people, they're all guys. And you might get the wrong impression. You might get the impression that it's only guys who do physics, who are good at physics. So I need a little parenthetical, it's not that, is what I want to make the point. And because I'm a scientist, I'm going to show you charts. So these are data. These are studies that were done by sociologists. What they did was they made a CV, a resume for job applicants. And they gave them to professional scientists. And this is not, back in the 1950s. This is 2012. They gave them to scientists and said, who would you hire? And they did this for different people. Sometimes the person's name was John. Sometimes the applicant's name was Jennifer. On the left, you see how they were ranked if their name was John, and on the right, you see how they were ranked if their name was Jennifer, for competence, hireability, mentoring, and the salary that they would be paid if we did hire them. Exactly the same resume, just different genders for the applicants. And by the way, so you see that women were consistently biased against, even if their accomplishments were exactly the same as those of the male applicants. And by the way, the bias was absolutely the same for the male professors and the female professors. Everyone discriminated against women trying to get a break coming into science. This is a problem that we have to do something about. The good news is we are doing something about it. This graph is the percentage in the US of women in PhD and bachelor programs in physics. And it is going up like gangbusters. And it's not, if you look at the percentage of women in doctorate programs in physics from 1965 to now, it's gone from 2% to 16%. This is not because the intelligence of women has increased by a factor of 8. This is because women and some men have complained about it, and we're gradually doing better. So 100 years from now, when you come back to the RI, because by that point we'll all be immortal and uploaded into the singularity, and you hear about new results in physics, there'll be just as many women having contributed them as guys. So that's the end of my little mini talk in the middle there. Now, let's build a Hadron Collider. Building something like the Large Hadron Collider is not something you are ever trained to do, because it only ever happens once in the history of the universe. You notice that this is a pretty big part of one of the experiments. This is part of the CMS experiment. Many of the size constraints of the components that these experiments used come from the fact that they knew that at some point they would have to be trundled through a road of a small French village on the way from wherever they were built to the experimental site. So this is as big as it could possibly be to get through there, and no bigger than that. Then you would dig a tunnel, you would dig a tube where you could lower the pieces down. So you have thousands of these magnets that are the strongest magnets, well, the largest scale magnetic fields ever built to make superconducting magnets. You lower them down, there's very little tolerance, it's a few centimeters on both sides. You do this for thousands of magnets. Sometimes, as you're building this, they had to build a new tunnel because there's two experiments, ATLAS and CMS, that do the general purpose physics at the LHC. They didn't flip a coin, but let's say they flipped a coin and one of them got to be close to the main CERN campus, the other is at the other end of the ring. CMS had to be at the other end of the ring, so they needed to build a new tube to lower CMS to the ground, and they only went a couple meters down when suddenly ancient Roman ruins. I mean, it's in the middle of the France-Swiss border. Civilization's been going on for a long time. So the physicists get kicked out, the archaeologists get brought in for 6 months, as you carefully look through, and they found coins in this little establishment from London. as well as from Rome and from elsewhere. And also the streets of the village of Cesi, where the CMS actually exists now, are parallel to the streets of the ancient Roman village that were there. So these streets never went away. They were just, improved and built upon over the years. Eventually, the archaeologists do their job. They clean up. You keep building. You put it all together. You turn it on, and it explodes. 10 days after the LHC turned on in 2008, there was an explosion. 6 tons of liquid helium were splashed around the floor. Had anyone been standing there, they would have been hurt pretty badly. Safety procedures were in place. No one was hurt at all. But the LHC shut down for over a year. This was an accident, of course. It was not planned. But it was an accident that would have kept happening if they had just tried to push the thing. So instead, they shut everything down. They went in. They fixed everything, tightened the screws, checked the wires. And as a result, when they turned back on in 2009, the machine worked really, really well. That extra year really sort of focused everyone's attention. And since 2009, the Large Hadron Collider has been going like gangbusters. There are, as I said, these 2 experiments, ATLAS over here that looks like an alien spaceship, CMS. Both of these are very big. CMS is a little bit smaller than ATLAS. Neither one of them would fit inside this room. If you want a little sense of scale, I circled the people here. So that's a person. That's a person. This is a particle physics experiment. This is a beam where protons are going to come and smash into each other. These are giant magnets that help you detect the particles. Like I said, the world is changing. Here are the bosses of these 2 experiments. Fabiola Gianotti is the boss of ATLAS currently. The boss is known as the spokesperson in the particle physics lingo. Joe Incandela from UC Santa Barbara is the spokesperson for the CMS collaboration. But each collaboration is over 3,000 physicists. When CMS or ATLAS writes a scientific paper, there are 3,000 authors. This is the tradition in particle physics. Everyone who works on the experiment is an author of every paper written. Not that they have read the papers that they are authors on, but they are in the list of authors. It is in every way overwhelming, the LHC, CERN, particle physics as a whole. It is a truly impressive monument to human beings trying to figure stuff out, trying to figure out how the universe works. They put together this amazingly complex machine. It could have just not worked at all, and it worked amazingly well. Some of the aspects of it are not in any way gargantuan. My favorite part of the Large Hadron Collider is the source of protons. So a proton is just the nucleus of a hydrogen atom. So literally, this fire extinguisher-sized thing is like this big. It's full of hydrogen. It is the proton source for the Large Hadron Collider. They open the little spigot, protons come out. They zap the protons with electricity, separate the electrons off. They start accelerating the protons, and you're off to beat the band. Hundreds of trillions of protons around the LHC, but there are many more than 100 trillion protons in a canister of helium. This canister of helium is enough to charge up the LHC with protons for about 10 billion years. Protons are not the scarce resource when you're building a particle physics laboratory. So you take these protons, you accelerate them to 99 point, et cetera, the speed of light, smash them together, and this is what you get. You usually get a mess. You get a lot of particles coming out, and the particles do not have little labels on them saying, I'm a muon. The particles come out with different velocities, different susceptibility to colliding with other kinds of particles, different electromagnetic fields, and so forth. So there's a tremendous amount of effort put into analyzing the particles that you see. Almost all of the collisions give you absolutely boring results, because we understand physics so well that the known physics is almost every collision. If you were to take the data produced at the LHC and write it all to disk, you would fill up the largest database in the world in a matter of a couple of seconds. You can't do that. Even CERN cannot write data to disk that well. So they throw out about 999,999 out of every 1 million events. They keep the data from about 1 event in a million. So you need to be very careful to try to look at the good data. You look at the data very, very quickly, look at the event, say, is this potentially interesting? Okay, I will keep it. This one is very interesting. You see the little blue lines. These tiny blue lines are electrons. These long blue lines are muons. That's a hard thing to make at a proton-proton collision. It's not impossible, but it's hard, so you keep this one, put it on your web page, try to analyze it. What you're looking for is the Higgs boson, and there's two problems when you're looking for the Higgs boson. One problem is, because of quantum mechanics, you don't predict exactly what the Higgs boson decays into. You predict the distribution of things it can decay into. It could decay into bottom quarks, W bosons, gluons, etc. So you have many, many different channels, as we say, to look for, things that could be produced by first making a Higgs boson in this collision, and then the Higgs boson very quickly decays. You never see the Higgs boson directly. The Higgs boson decays in about 1 zeptosecond. You don't need to know what that is. It's a very tiny period of time. You could see things that happened on timescales as small as a millionth of a second. A zeptosecond is way, way tinier than that. So you never see the Higgs boson. You only see what the Higgs boson turns into. And when the Higgs boson turns into something else, the other problem is there are other ways to make that stuff. So that if the Higgs boson decays into 2 muons and 2 electrons, there are other ways you could have created 2 muons and 2 electrons. So it's a matter of statistics. So sometimes people say, looking for the Higgs boson at the LHC is like looking for a needle in a haystack, right? This is a cliched analogy. It's also not accurate. Looking for the Higgs boson at the LHC is like looking for hay in a haystack. It's like looking for slightly more hay of exactly a certain length than all the other hay that you have. Because if you create, 2 W bosons by a Higgs decaying, well, you could have done that many other ways, but maybe there's a few more than you expected because the Higgs boson decayed also. So the kinds of things, after many, many hours of genius-level manpower go into this, this is what you are left with. If you look at the book that I mentioned that I wrote a book, these 2 plots are in the book. These are the only pictures in the book where my editor at first said, no, we don't want to have that. That looks too sciencey, looks too complicated and scary. And I said, we paid $9 billion for these plots. We should put them in the book. And so he said, okay. $9 billion, the price of the LHC. These are the exciting results from the LHC. As you see, this is the number of certain kinds of events. The particular events we're looking for is when you smash the protons together and 2 photons come out. It's actually not that easy to get only 2 photons and no other junk coming out when you do that. So this is a rare event. You see that even though you have hundreds of millions of collisions per second at the LHC, you only get thousands or hundreds of events of this type. And then you count up the total amount of energy in those photons. And this is in weird particle physics units. So we don't measure energy in kilowatt hours or something like that, because then ordinary people might understand what we're talking about. So we measure them in billions of electron volts. And so for 100 billion electron volts, 110, et cetera, here are the number of events like this that we produced at the ATLAS experiment. Here are the number we produced at the CMS experiment. And you wouldn't notice it except for the fact that the helpful particle physicists have drawn a curve through it. But there's a bump right there and right there. That bump is what we call the Higgs boson. There's a new particle. Why is there a bump there? Because all the other stuff is just sort of random nonsense that comes out because you've collided protons together. The bump comes because there's a new way to make those photons. First, you make a Higgs boson, 126 billion electron volts worth of mass, and then the Higgs boson decays. So you look for new particles by bump hunting, by looking for slightly more events of a certain kind than you would predict if that particle weren't there. You're looking for hay in a haystack, slightly more hay of a very specific length. Now, even though these bumps don't look that big, there's 2 experiments. That's very, very important, right? So one experiment cannot just be pulling the wool over our eyes. And they've analyzed to death these data with very sophisticated mathematical machinery. And there's no question that this bump is real. And the only way that we can think of to make it is a new particle with precisely that mass, a particle that has all the properties of the Higgs boson. We're not 100% sure yet that it is the Higgs boson that was envisaged by Peter Higgs and his contemporaries back in 1964, but it walks and quacks just like the Higgs boson does. It's certainly a very Higgs-like boson. So somebody is going to win the Nobel Prize. We don't know who. Actually, I don't even know for sure if somebody will win it. What I do know for sure is that this kind of discovery is better than Nobel Prize status. Some discoveries get elevated in importance by having a Nobel Prize attached to them. Sometimes the Nobel Prize gets elevated in importance by becoming attached to certain discoveries. No question in the world that discovering this new particle is worthy at a science level of recognition such as the Nobel Prize. The problem is, there's a tradition among science Nobel Prizes that they can't give it to organizations, they can only give it to people, and they can't give it to more than 3 people for any one thing. So think back, how many people are on the experiment? 3,000 people on 2 different experiments. How many people came up with the idea of the Higgs boson? Well, 6, 7, 8, depending on how you count. Never 3 or less than that. So nobody knows what will happen. How many people built the LHC? Many thousands also. There's at least 3 Nobel Prizes that deserve to be given. One for predicting the Higgs boson, one for finding it, and one for building the Large Hadron Collider in the first place. I have no idea what actually will be done. No one's paying me to answer that question, therefore I'm not going to do it. But it's also not the end of the road. We've been very, very excited by discovering the Higgs boson. I mean, this is literally, the idea of the Higgs boson came here on Earth before I did. I have never been alive at a time when we didn't know about the idea of the Higgs boson. That's how long we've been looking for it. That's why Peter Higgs got a little misty at the seminars at CERN when it was discovered that they actually found it. I mean, here's a young guy, right, graduate student, postdoc kind of level, and everyone doing this at the time was very young. And they were puzzling with this problem, why are the nuclear forces short range? And they came up with this idea, and they wrote it down, and everyone ignored them. And then over 40 years later, someone says, oh yeah, here it is. We paid $9 billion and we found it. That's just science at its absolute working best. But we're not done. The Large Hadron Collider was not built just to find the Higgs boson. It was built to find new particles. It just shut down for the moment. It's in a shutdown mode for 2 years now. Well, they tighten the screws once again, and they're going to lift it up to a much higher energy. So the LHC will turn back on in 2015, and we're going to be peering at a regime of physical reality at which we have never peered before. So we're hoping to discover new things. This is one example of what we're hoping to discover. Twice as many particles. If you wonder that maybe we just don't have enough elementary particles, there's an idea called supersymmetry that says for every kind of particle we know of, there is a friend called a superpartner. We didn't go through this because I'm just giving a 1-hour lecture, not a series of 12 one-hour lectures, but there are matter particles in the universe called fermions, and there are force-carrying particles called bosons. And in the real world, the fermions we know bear no obvious relationship to the bosons we know. But supersymmetry says that for every boson, there's a fermion partner and vice versa. So because in the standard model of particle physics there is no relationship, the idea is that there are new superpartners, and just to keep our spirits up while we're looking for them, we invent clever names. If you have a fermion, its bosonic partner gets an S at the beginning. So there are squarks for the quarks. So there are spotum squarks and so forth. The bosons, their fermionic particles get an eno at the end. So there's a gluon, a gluino, W and Z, wenos and zenos, and so forth. And we're looking for these superpartners. If they exist, and if they are within our reach, the LHC will be able to find them. They might not exist. It turns out that the idea of supersymmetry is not just a cool idea. It has all sorts of beneficial consequences. It helps explain the dark matter in the universe. It helps explain the mass of the Higgs boson. It is part and parcel of superstring theory, which is our most promising theory of quantum gravity. So many people want supersymmetry to exist. The universe does not care what we want, you may have noticed. So we may or may not find it, but it is one of the things we're looking for. As a bonus, one of the things that supersymmetry predicts is that one Higgs boson is not enough. If supersymmetry is right, the world has 5 different Higgs bosons. So even if the particle we have found is a Higgs boson, it may turn out to be only 20% of the Higgs bosons that we will find in the years to come. So we're very optimistic that cool new things will happen. Of course, this is only an idea. This is not data. Here is data. Here are data, whatever you want to say. We know that the standard model of particle physics is not the end of the story. for the universe. We know that because the standard model of particle physics makes up what we call ordinary matter. It explains you and me and the table and the air and the sun and the moon and the stars. It does not explain the universe. Because we can map out the gravitational field of stuff in the universe, and we see pictures like this. This is a map constructed by looking at the deflection of light through galaxies scattered throughout the universe. We can basically weigh the universe. And what we find is there's a lot more stuff than we can possibly account for than in the standard model of particle physics. We call the extra stuff dark matter. It's not quarks, it's not electrons, it's not neutrinos or Higgs bosons. It's something absolutely new. So we can't be done with particle physics. There's some new particle called the dark matter particle, or maybe 20 new particles called the dark matter sector of many different particles. We don't know yet. We're looking underground for dark matter particles to bump into things. We are also trying to create dark matter or other particles associated with the dark matter at the LHC. So it's absolutely clear, not just a wishful thinking kind of thing, that there must be new physics out there. The LHC is on the mark to try to search for it. We'll have to see if nature is kind or a little malicious to us. In the meantime, if you don't tune your telescope on the rest of the universe, if you stay in this room and you think about your life, as long as you're not a professional physicist or astronomer, if you think about the physics, the laws of physics underlying the phenomena that you experience every day. So the table, the chair, the sun shining, you and me, rabbits and bunnies and trees and grasses and bugs and so forth. These are all made of particles described by the standard model of particle physics. There are no new particles you need to describe bunny rabbits. I can guarantee that, because if there were, quantum field theory says we could make them at the LHC, and we would have made them a long time ago. As long as quantum field theory is right within the regime of a bunny rabbit, we know the particles that make up the bunny rabbit. Protons, neutrons, electrons, the quarks inside them, and the four forces that hold them together. And the Higgs field filling empty space was the last piece of that puzzle. So on the last slide, I tried to emphasize that physics, particle physics, the search for the ultimate laws of nature, is nowhere near done. We know we have a long way to go. But as far as the fundamental physics underlying us, particle physics is done. We have done it. July 4th, 2012 was when we put the final piece of the puzzle of the matter that you and I are made of together. We've been looking for this for 2,500 years, since Democritus, and we've finally been able to do it. We're not done yet. There are worlds beyond our everyday experience, but this moment in history is not going to be forgotten. 1,000 years from now, we will remember the day that we found the Higgs boson. That is why it is such a big deal. Thank you.